Hey everyone, so today we're going to go over a little bit of a simpler question, which is the LeetCode 2 sum question. It's a very popular question, but it holds some important principles. Let's get started on it today. All right, so what is the question? The question is, given an array of integers, nums, and an integer target, return two indices of the two numbers such that they add up to target. So if your first index is I, your second index is j, we want to find I and j such that, let's say, nums I plus nums j is equal to the target. We can assume that every input would have exactly one solution, and we can't use the same element twice. We can return the answer in any order. So that there's certain guarantees that we're given that kind of help us in terms of like minimizing the number of edge cases to kind of consider. But let's get started here. So let's take this first example and see if we can just kind of brainstorm how to do this. Go this here. All right, so today I'm using a new. I'm gonna be using Lucidchart. Last time I used Sketchboard.io, but I kind of like Lucidchart. This is a very I'm on a free trial, obviously, but it's a very professional way. I use it at work, for example. Just like drawing diagrams and kind of conveying pictorially conveying ideas and stuff. All right, so let's say we start with this nums array, and then we have this target of 9. So the question, it's a two-sum question, obviously. So we're looking for two indexes such that the elements at those indices add up to the target. So one of the most, I don't want to say easy because that's kind of like, this question might not be easy for someone who's just starting out, but one of the most common paradigms to check two elements of an array is a nested for loop, because basically we want to check the entire list, right? For those two elements that add up to 9. So in order to do that, one thing we can do is use a nested for loop. So what does a nested for loop look like? So if we kind of draw this out here, I'm just going to move this out here. Right, so 2, 7, 11, and 15. Basically, we want to check 2. Right, zoom in here. We want to check 2 against every element. So check 2 against 7, 2 against 11, and 2 against 15, right? So I'm going to write that down here. Check 2 against 7, 11, and 15, right? So that'll cover all the possibilities for the first element, right? But once we're done doing that, we also want to check 7 against 11 and 7 against 15, right? So say this, check 7 against 11 and then 15. So you can kind of see what the pattern is here. So we're kind of iterating through the list, and then for that element, we're checking the rest of the list. So naturally, the next one would be check 11 against just 15, right? So in this case, once we check 11 against 15, then that's the entire array. So basically, you can kind of see like you're kind of walking along the list. I keep on using list and array interchangeably, so just know that I mean I mean one or the other. So I check 2 against 7, 2 against 11, 2 against 15. Done with that. Done with 2. Next, we check 7 as the first element, and then 7 against 11, and 7 against 15. So this is essentially what a nested for loop does. So what does a nested for loop look like? So if let me drag out another text here. So let's back up and think about just like a normal for loop, right? Normal for loop, what does it do? It just simply iterates through the list. So let's build out a normal for loop. So in Python, it's for I in range, length of the array, nums minus 1. Let me drag this out so it's like a little easier to see. right? So this is basically, and then we do something with nums I here, okay? So this is basically a normal for loop in Python. So essentially what you're doing is you're, for each index in a list, you're starting at 0, and then that counter I increments to 1 to 2 to 3. So this might be a little easier to see actually in if we just print this out, and let's use the LeetCode IDE. Okay, so let's look at what happens when we just simply iterate through this list here. So the code I have is for I in range length of nums. So this is the same as saying this. Oops. It's the same as saying for I in range 0 to length of nums. So this is basically saying I will start at 0 and then iterate through the listed array until it hits the last element, which is length of nums -1. So this goes up. This goes from 0 up to length of nums -1 inclusive. I know it's a little unintuitive because this is length of nums, but that's kind of how this function works. So let's go ahead and just print this out and see what this gives us. So print I nums I is pretty straightforward. This might be a little just too obvious for some of you folks. Let me move my face up. All right, run code. Let's see what it prints out. Right. So ideally, it should print out the indexes on the left column, which we have 0, 1, 2, and 3, and then the values at those indexes. So 2, 7, 11, 15, which is just the list here that we have, right? All right, so that's all good and not too bad. But let's go back to our diagram, because how does this factor into our question, right? So let me wait a second here. So essentially what we're doing, I kind of wrote it down in a very kind of notesy unofficial kind of way, but for our brainstorming purposes. So I already wrote some stuff earlier here. Let me get rid of this. So basically what we're doing, right? So I is our for loop that we made here. So we're taking I, starts at 2, and then I iterates throughout the list, right? That's all good and fun. Well, how does it matter our question? Well, for our question, for each element at I, we want to check every other element after it, right? Because then we're checking basically every pair in this list. So let's say it starts at I, right? And then say we have another loop, right? Let's call it just J, right? So now we can check I and J, which is 2 and 7, and check if it's equal to our target, which it is in this case, so we return it. But let's say it wasn't. Then we want J to continue on, right? Continue on all the way till the end. So J is now 11, and then J is now at 15, right? So say we still haven't found the target yet. What do we do now? Well, we want to continue checking the rest of the elements, right? So we've checked 2 against every element. Now we want to check, start with 7 and check it against every element. That way we cover all our bases, all our possible pairs throughout this entire list. So I will start here, and then similarly J is going to start 1 after I, and then J is going to end up here, right? So you can kind of see how this keeps going, and it's going to basically stop at this point here when I is at that element and J is at this element, right? So our outer for loop, which we just kind of made here, is going to stop actually at, now we can actually start coding this up, at least the iteration part of the 2 indices is going to start 1 minus the length of the array, because we want to stop at 1 element before the n, right? Because I is going to stop at 11. But J is going to stop at where I previously stopped when we were just going through that example. But notice that J is always going to start at I plus 1, right? So we can kind of code that up here in this, in the bottom part. For J in I plus 1, right? and then j is going to start at the very last element. So what we had before here, right? So this is basically uh, our iteration loop. That's going to form the foundation of what we had. There's a lot of construction going on. I don't know if you guys can hear that. But let's just go ahead and just like print this just to kind of see, exactly what's happening here. Okay, so again, first column is I, the outer loop. Second column is j, which is the inner loop. So you can say it looks at the index 0, and then the index at 1, which is 2 and 7. I know a lot of numbers being tossed around here, but next it looks at the element at 0, so I is fixed, and it looks at the element at index 2, so 2 and 11, right? And you kind of read the rest of this, you can kind of see that it checks every possible pair in the way that we kind of defined earlier. All right, so that structure of a double for loop is set up. So now we just have to do the actual, implement the actual logic, right? Because now we can actually check every possibility, every pairing of elements at I and j. So what are we doing? We basically want to check if the elements at I and j equal to the target. So that's pretty straightforward to implement. So simple conditional. So if nums at I, the first element, plus nums of j is equal to the target, then we simply return the indices. And it doesn't matter which order we return the answer. And the reason they say this is because just to simplify it, and also you can imagine you can iterate from the front, which we are doing here. You can also iterate from the back because it's kind of symmetric in that way. So in this case, since the ordering doesn't matter, we simply just return I and j without any. We don't need to add any additional logic to like check the ordering or take that into consideration. And yeah, so that's the meat of it. Now, some astute observers might recognize that. What if it never satisfies this condition of two elements adding up to the target? Well, in that case, we could return, and it kind of depends on the question itself. But in this case, the return type is a list, as you can see. So it might make sense just to kind of return an empty list. Again, this is something you would ask your interviewer or check the question. Now, if we do check the question, we do see that only one valid answer exists, which I think this is actually implying that there is guaranteed one answer. So this is probably not even necessary, right? So we can actually kind of just check this when we actually run the code. And again, I should say this is not a real mock interview. Like in a real mock interview or interview, you would do like a dry run. Essentially, you would list out in the comments like when j is 1, what happens when I is whatever it happens. Like you're not actually running any code, but this is just kind of like a tutorial to kind of explain the concepts. So we'll kind of ignore that for now. I'll do that in another video. All right, so this works. So we can just go ahead and submit this and see how it works. You can see that I've submitted earlier today. I was doing some other testing. Okay, so you can see that it's actually quite slow, right? 6 seconds, which is slower than like 90 or faster than 9% of submissions, slower than 91% of submissions. So the reason behind this is that you can imagine for each element in an array, you're checking against every other element, right? So you're kind of like seeing each element like exponentially a large amount of times, because you can like for this array, it's relatively small, but you can imagine for what if this array were like 1 million items long, right? That means for each element, you're continually checking it against you're continually seeing an element, right? So like you can in terms of we can kind of analyze this very simply. Let's say the outer loop, we're checking n elements, right? N for the length of the array, checking n elements, where n is the length of nums, right? So we're doing this, but then for each of these n elements, and this is where we're going to the inner for loop, we're checking n minus 1 elements, right? Because we're checking starting at I+1 to the end. Actually, this is also n minus 1, right? Because we're checking it up until the second to last element here. So this is actually the same. Yeah, it's also checking n minus 1 elements, where n is the length of the list. So if you multiply this together, you'll see this becomes n squared elements that you're checking. So in terms of like time complexity, which I'm not sure if you guys have or know about, we can talk about that in another video. But in terms of time complexity, that means it's O of n squared time, because you're basically checking all the elements. In the worst case scenario, where let's say you like don't have a match until the very end, until very like the match is at the very right side of the array, then you'll have gone through n squared elements, right? Technically, it's n minus 1 times n minus 1 elements, but like this becomes quadratic, right? So it's n squared minus, it's been a while since math, but technically n squared minus 2n plus 1 elements. But for analysis purposes, n squared grows so much faster than 2 times n, because 2 to n is linear, right? You can imagine like a line just kind of with a slope going up, but n squared is kind of exponential. So you imagine like a u, like a u going up. So it's just so much faster that we kind of ignore these two. So you can say it's what they call O of n squared time, which is super slow. Like when you're doing interview questions, O of n squared, unless it's like a question that involves like a triple for loop or something else, usually O of n squared time is pretty bad, I would say. It's not an ideal answer, but again, it depends on the question. But like for these kind of questions where you're checking 2 elements, like O of n squared is pretty not ideal, right? So let's think about like a more efficient solution then in that case. So a more efficient solution, let's get rid of this. We'll kind of try to reset this. Okay, so a more efficient solution. All right, let's go back here. Let's go down. I will copy and paste this. Right. So another way of doing this is, let's take a look at this question. Obviously, that's what we're doing. But let's say we're iterating through the array, right? Say we start at I is 0, so the first element. Well, we see 2, right? So we see 2, and we know that 2 is in the array because we've already like passed it. So that means that you can kind of think about this just from like a very like general like non-algorithmic perspective, I guess, is to say, okay, we've seen 2 and our target is 9. Let me just, so we don't forget, I'll write the target here. Target is 9, right? Oops, I'll just make it same line. That means, so we see 2. It means we want to see 7. Like when we see 7 in the rest of the array, that's when we know that there's like a match, right? So it means we want to see 9 target minus 2, which is 9 minus 2, which is 7. Let me move this out so it's a little more on the same line. Why isn't it letting me do that? That's a little better here. Okay, there we go. Stretch this out. Okay, so we want to see target of 7. We want to see 7 in the rest of the array, right? So like that way, if we're keeping track of what we've seen, or not what we've seen, but if we're keeping track of what we're looking for, then you can kind of see that we don't need to iterate through this array twice, like in a nested fashion. So, right, because say we see 2, since we have 2, we know that we are looking for 7. So what if we somehow stored 7? That way, when we go to, let me go ahead and move this down here. That way, when we iterate to the next element of the array, oh, and then we see 7. That's great. But since we've stored 7, we know we're looking for it. We can kind of do some kind of check and say, all right, 7's here, and we've already seen 2, so that means we found a match, right? Because this is much faster. This would be much more ideal than like doing some kind of for loop to check every like element like multiple times, right? So how do we do that? Like, how do we, like, first of all, store what we were looking for, which in this case is 7. But also, remember, we're returning to index. So we also want to store the index of the first element, right? In this case, which is 0, I is 0, right? So let me write that down. So we want to store what we'll call it seeking, right? Which is target minus the element, or we are seeking. Also, we want to store the index of the it's called the matching element, right? Which in this case is 2. Index 0 for value 2, let's call it, right? In this example here, which is 7, right? So how do we do that? Well, there's a very simple data structure that allows us to do that, which is called a hash map. So I need to go ahead and change this. I'm not sure why the alignment got changed again. So what if we use a hash map to, so hash map is basically represented by, usually by like curly braces. So essentially in a hash map, you define a key and a value, right? So it's kind of like a lookup. So it's saying, let's say A points to like 3, right? Let's say this is our hash map, right? That way in a code, when you like try to access it, usually it's by these square brackets, it'll return 3. So it's like a quick lookup. And there's reasons behind it, but this is a very fast lookup. It's like basically saying, as soon as I look at the hash map, given a key, which in this case is A, in constant time, which is like very fast, it returns what that key maps to, which in this case is 3, right? So this is a very powerful data structure. The trade-off is that you do have to store like space in it, like there's extra space, because you're obviously creating a new hash map and you're putting elements, you're throwing stuff in there. So it does have that element of using extra space. But in terms of time access, like how fast it is to access a key, it is quite efficient. So in this case, what if we use the hash map, but instead of A and 3, what if we somehow we want to like maybe store what we're seeking and also the index of the element that is matches with that seeking. So we want to be able to access the seeking value fast, right? Because remember here, like when we reach I is 1 second value, we want to say, oh, is 7 in this whatever data structure, in this case a hash map. And the way to do that, like I just mentioned, is to make this the key. So let's make this seeking value the key, right? And let's point it, because we want to store the index of the matching element. Let's point it to the index of the matching element, right? So in this case, in our example here, let's call this, let's not call this hash, we can call it seeking hash map, just to be super explicit. Is, right? So let's start from the beginning. So at I is 0, index 0, we see 2, but we're seeking 9 minus 2, right? So that's 7. But we also store the index of the matching element, which is 2, because 2 matches with 9, or sorry, with 7, right? That way, when we access it later, we can get the index super quickly because we need this index to we need to return this index in our answer, right? So this is basically going to be like the foundation of the more efficient solution. So basically what we're doing is we're iterate through the list, and first thing we want to do is check if before we do any of these like adding any elements to the hash map, we're looking to see if we have a match first, right? So we're seeking if the element is in the seeking hash map, then basically we return the two indices, and we can write the code out, right? And we'll have access to these two indices, right? Because like I mentioned, the seeking hash map points to the first index that it matches to, that the current element matches to, and we're iterating through the list. And since we're iterating through a list, we have access to the current index. So we have access to those two indices, right? So this is yeah. So this is like the happy scenario when we see the match, right? But what if we don't see the match? If we don't see the match, that means we're still looking. So we want to put the element that we're looking for in the hash map. So in this case, if this condition is not met, then we want to put what's it store target minus let's call nums I. Let's call it. This is a very unofficial like pseudocode, by the way, but hopefully the point is still there. So basically, we want to store target minus nums I in seeking hash map. Here, yeah. So this is basically our core algorithm here, and we can flesh it out with the code, of course. So let's go ahead and copy and paste it, and then boo boo. And we'll just kind of put it in the bottom here. So basically, iterate through the list index I. So for I in simple iteration like we did for the double for loop in the other approach, length nums, right? So now we have access to the index. If element is in seeking hash map, so let's go ahead and initialize the seeking hash map. Curly braces, that's how you initialize it. So if nums I in seeking hash map, this is just a syntactical thing. I'm not going to focus too much on like Python language, just because you can kind of look that up yourself. But if there's interest in going through that, then we can do that in probably like a separate video or something, right? Okay, so we want to return the indices, right? So what's the first index we had? First is arbitrary. Like again, the order doesn't really necessarily matter here, like they define or mention in the question. So let's just return I. And remember, in the seeking hash map, the key is what we're looking for, the value we're looking for, and the value is the index, right? So for the second index, we want to return this index, which is going to require us to look in the seeking hash map for the value, right? Yeah, and then look in a seeking hash map for the key, which is what we're looking for. And this will return to us the index of the first match, like the first element of the pair, right? All right, so that does it for this. Let me make sure my brackets are good. Okay, I think it is good. So now, what if we don't find a match? Then if we don't find a match, then we store target minus nums I in the seeking hash map. So I'm just going to do this. So target minus nums I. Actually, it could be even, let's just be really explicit here, just to make it more clear. This is the value we're seeking, and we put it in the hash map, and we point it to the current index I, right? Yeah, and that should be it. And there's no, remember, our happy condition is here. We can return an empty list for no solution, but again, it seems like we're guaranteed one valid answer. So let's go ahead. I'm gonna get rid of this notes here because we already have it in the other doc. Let me run this code. Yeah, so this one works. Submit it. Okay, nice. So you can see this runtime is magnitudes faster, at least 100x faster, at least from this run, than the nested for loop solution. So in terms of like the runtime of this, if you look at the code itself, we're just iterating through the length of the entire duration or span, I guess is a term of the list just once, right? We do this like, if you look at the rest of the code, we do conditional checks, but that's just once for every element in the array. Also, we do access the element, but again, like I mentioned earlier, this is accessed in constant time. Like it's not a function. This accessing is not a function of how long like the hash map is. Like just simplify it. Like it is not necessarily a function of that. Like this hash map could be quite long. You can still kind of assume that it's independent of how long it is. Like it won't be slower because of the length of how many elements you're storing in here. I think realistically speaking, or from like a theory perspective, there are some differences, but for like LeetCode purposes, that's something that you can kind of ignore for most cases. So ultimately, the in terms of like the analyzing how the runtime, this ultimately only looks at n elements. So looks at n elements. So we can kind of say this is O of n runtime. Yeah. Yeah, so this is the more efficient way of doing it. I think there are some other ways of proceeding with this question, of doing this question. Some like funky ways. There's like some less efficient ways where you can like sort it and do some kind of binary search. But these are the most common. This is my preferred way just because it's kind of short. It's, I think, clean, and also uses a data structure that a lot of people don't. I don't want to say don't take advantage of, but it's one of my favorite data structures, just because of the ease of access, the efficient access of the key. So yeah, this is twosome. Yeah, let me know if you have any like questions or if there's anything I could have explained better or anything like that. And yeah, thanks for tuning in.